The next presentation will be on concrete pavement evaluation for restoration by John Donahue. John Donahue is the Construction and Materials Liaison Engineer with Missouri DOT. He is an active member of the AASHTO Committee on Materials and Pavements.
Thanks for the introduction, Judy. I'm going to dive right into this. Basically, what I'm going to talk about is just things I've learned from an accumulation of experience doing evaluations of concrete pavements in Missouri. We kind of had a break point around the year 2000. Before that, we were pretty good at doing full depth repairs on virtually everything or overlaying it in old concrete pavement. And a lot of times we didn't necessarily need to go as far as we did. So we started to employ some less intrusive preservation techniques such as partial depth repairs, dowel bar retrofits, cross stitching, different techniques that would also extend the performance life of the pavement. This is an example, and you might have heard some ACPA presentations in the past talking about what they call the buried treasure concept. And that's essentially an old concrete pavement that's been overlaid perhaps multiple times, and they go ahead and mill all the asphalt off. And lo and behold, the concrete pavement wasn't as in bad a shape as they would have thought. That was my experience on this particular case. This was about 10 years ago, a piece of I-35. And this was actually in an area of the state where we traditionally had a lot of decracking susceptible aggregates. So I expected to see a lot of decracking when the overlay was removed, but that wasn't the case. And so looking at this pavement, I realized, you know, if we could go back in time, we probably would have addressed this a little differently rather than covering it up right away when there were, you know, maybe perhaps just a few mid-panel cracks and some minor spalling occurring at the time. And so the mantra here is going to be only doing what's necessary. In case you're interested, this is Buffalo, New York here. That's exactly what we want to try to practice too. We go overboard sometimes with repairs, and I really call it an overreaction to what's out there. I'm going to kind of cover about 7 different topics related to doing the evaluations and kind of planning for the preparation of the project itself. First area I want to talk about is distress severity, basically covering the different levels of distress and how you react to what you're seeing out there. Full depth repairs, they're always going to be necessary in certain cases, but really they should only be used when your slab is shattered. And technically, a shattered slab is more than one crack. I've seen cases though where even a slab with 2 cracks though might possibly be salvaged, perhaps with cross stitching or dowel bar retrofit. But just as a general rule of thumb, yeah, when you have more than one crack across a slab, it's probably a good candidate to replace. Also, if you have severe spalling, either at the joints or at the working cracks for longer slabs, maybe beyond the point of economically doing partial depth repairs, and a full depth repair might be the right way to go. And then there's what I call the pavements with concrete cancer, basically decracking, alkali silica reaction, or even alkali carbonate reaction. Other things such as low air entrainment could also be a problem as well. But the concrete is structurally compromised by what's happening inside it. And it's really a ticking time bomb. And all you can do is try to buy as much time as possible with the pavement before you have to do some major rehab to it. Now this is a classic example of a shattered slab. Looking at it, no doubt about it, it's shattered. We've got at least 4 different smaller sections of the slab. Actually, in a way, this might almost function. I wouldn't leave it this way, but the fact that you've kind of quartered the slab may actually prevent future cracking from happening and the rest of it. But I'm not going to bet the farm on that, but I'm just saying is sometimes that actually relieves the stresses that started it in the first place, the cracking. And then here's a case of joint spalling. Maybe almost, well, I think technically you could even do some partial depth repairs here, but this is doing a lot of work with that. And you reach the point where the partial depth repairs would exceed the cost of doing a full depth repair. And you're probably just better off going with that. Here's decracking. We have a lot, well, not a lot, but we have an area of the state where our limestone is of poor quality. If we don't fractionate it to smaller sizes, the larger stone will tend to freeze and pop as water gets cracked in it, and water gets in it, goes through freeze-thaw cycles, and it usually emanates around the joints and the working cracks. And once that starts, there's really no going back. It's basically going to continue to fall apart, spall, and again, all you're trying to do in this case is buy time. And this is also a problem. In this case here, we took some cores, did a forensic analysis, found out low air content. It doesn't necessarily look real bad right now, but this will over time get worse and get to the point to where, again, you're probably going to have to do a full depth repair here because there's just internal degradation in the panel. This is what I call throwing good money after bad. They use, it's either Techcrete or Fibercrete, that hot pour elastomeric patch material. Outside the boundary of that patch, you can see more cracking occurring. So this is just kind of like a stopgap measure by probably our maintenance forces to address what they saw, but they weren't really getting everything that was going on. Obviously, the boundary of the cracking exceeded the patch repair area, and eventually that would start to get worse also. And again, you'd have to be back here in a couple of years. So would have been better off just doing a full depth repair across this, actually probably across both slabs. And sometimes you see stuff that looks bad, but it's not necessarily anything you have to go run out there and do. You can get small pop outs from shale, sometimes over finishing, like I think was in this case here, is you're bringing a lot of fines up to the surface and they erode, and then you get kind of that segregated look from the larger remaining aggregate near the surface. So probably this isn't going to get any worse. It's more of an aesthetics issue, which I'll talk a little bit about later in this presentation. Again, it may look nasty, but it's not really structurally, it's probably not structurally compromising the concrete itself. And a lot of times if you're doing an evaluation of pavement, you kind of have to make a judgment call. Looking at this here, you've got ways going from, I'd call slight into the moderate range of spalling at a joint. They've already done some crack filling there to try to fill in some of the gaps. But again, I don't really see much going on besides those smaller pieces that have broken off. I would probably, especially if we're trying to watch our money on the repair quantities for this particular project, I would probably let this go. That amount of spalling really isn't going to impact the ride, even if that's in the wheel path. You're generally not going to notice it as you drive over it. In this case here, you're getting into the range of severe spalling. You have a wheel go over that, they will notice that, and it could probably get worse over time as well. So to me, this would be an excellent partial depth. I think Kurt's going to go into some detail on different preservation techniques. So I'm not really going to talk about the techniques themselves too much. I will mention here, though, that there is a hesitation by a lot of people as far as not wanting to do partial depth repairs because they don't think that they'll successfully stick or adhere, the patch material will stay in the repair area. And pop-outs do happen occasionally when the surface prep isn't adequate and the joints or working cracks are not reestablished with form boards. So yeah, it can be done wrong. But I'm here to say that you can do a partial depth repair successfully in a concrete pavement. In this case here, this is the full width of a lane where basically it was probably, I don't have a before picture, but I'm sure what happened here was that we had a lot of spalling at this working crack. It was milled, and in fact, in both lanes, you can see the offset of the one on the inside or the passing lane. But looking at the driving lane there, you can see that you had the full width of that lane. That material was all removed, crack former was put in appropriately. The mix or the surface was prepped, cleaned adequately. And then after the mix was placed and finished, it took. And this particular project, we did about 1,000 of these type of full lane width repairs, partial depth repairs. And I think we had only about a 1% failure rate. So with following the proper technique, they are partial depth repairs can be a very successful repair technique. Another thing to consider is the location of the distresses. Here's a relatively old concrete pavement. In this case, the crack pretty much runs through the center of the lane. So it's kind of in an ideal location in that it's about as far away from either wheel path as you can get it. I would probably just leave this alone. If anything, I might do cross stitching if you have a concern about possibly that crack opening up. No evidence of faulting across that longitudinal crack. So really, it's a stable pavement. All you're dealing with is that crack running down the center of the lane. It may not look pretty, but again, if you're trying to watch the budget and not go overboard on repairs, this is one that I would also take a pass on as far as doing any type of repair to. Something that happens occasionally is that, and a lot of times this is the result of late sawing, you may wind up with a longitudinal crack that forms within a few feet, or well, maybe 3 to 4 feet off the center line, usually just outside the zone of influence of the tie bars across the center line joint. I mean, it's probably close to the wheel path, but again, it's a pretty tight crack. It's not even showing any signs of further degradation at this point. Maybe keep an eye on this for the future. But again, if I'm estimating quantities here, I'd probably leave this alone. At a minimum, or I mean, say at the most, I'd probably consider doing cross stitching here just to keep the crack tight. But other than that, you wouldn't really have to do anything. Definitely not replace it. And interesting phenomena I came across years ago when I was curious about what was happening in the crack and in the saw joint. In this case here, you can see there's 3 panels in that schematic. The first panel, the crack formed normally where the joint was sawed down the center line. The next one, the next panel, the middle panel, you had an uncontrolled crack, or in the saw joint and in the crack. You could see that the saw joint, the crack was not, there was no crack forming through, it didn't activate through the actual sawed center line joint. It did obviously go all the way through that crack, the parallel crack though in panel 215. So it's a full depth crack there. Now, where at the confluence of the crack and the saw joint in panel 214 to the right side there, that core was taken beyond the point that they joined together. So you would think that perhaps the crack was running vertically up and down through there, but it wasn't. It was actually still kind of almost like the tail of a tornado or something, where it's not really, it's kind of dragging behind the full body of the tornado, and kind of a similar phenomena here. But the point I want to make is because of that horizontal crack there, you have an area where potentially you could have spalling. Looking at this to estimate repairs, panel 215, I probably wouldn't do anything other than cross stitching. If I'm going to do a full depth repair anywhere, it would be in panel 214, where you have the crack and like I said, the confluence of the crack and the joint, and you do have a higher potential for spalling to occur later. So that's the area that I would probably do a full depth repair on. This is just showing something. This was kind of ad-libbing. We had this was actually like a 5 or 6 inch bond of the concrete overlay with sawed into 6x6 panels. The contractor left some of their heavy equipment on the shoulder, and it was just on the edge of the pavement. That's what caused those cracks. To mitigate it, we could have made them replace these, but we allowed them to do epoxy repairs. It's not something we do often, but again, in this particular situation, we allowed it. And I've been out there several years after this was done, and they still seem to be holding up all right. The age of the concrete pavement. Here we have a 65-year-old pavement. You can see one continuous longitudinal crack running down there. If you think about it, it took 65 years to get to that point. By the time you really have to come back in and replace it or cover it up, it's doubtful the crack is going to deteriorate much worse than what you're looking at. So by taking that into account and also considering the traffic, I think this was a US route that ran parallel to a newer interstate route. And when the interstate route opened, it basically siphoned off the traffic off this US route. So it kind of settled into old age as a lesser used road. So again, truck traffic was not a major concern here. Rather than going in and doing wholesale replacements, at the most, maybe do some cross stitching, maybe a little crack sealing or crack filling along there. That's probably all you need to do. Here's a 45-year-old jointed reinforced concrete pavement. In this case here, we had some minor spalling at the joint, surprisingly for 60-foot joint spacing or 61.5-foot joint spacing. Very little mid-panel cracking, so it appeared to be very stable And in this situation, working with the designers on this, we decided just to do perhaps some partial depth repairs where we had a little more severe spalling, and diamond grind it for what this road. And you can see it's kind of it's serving an industrial area. So there's a lot of trucks on here, but it really did well over its design period. There really weren't any mid-panel cracks, which surprised me because usually for these type of pavements, there almost always are. Now here's kind of the other end of the spectrum where we had a fairly young pavement, no concrete pavement, 7 years old, whether it's full depth pavement or an overlay should be doing this that quickly. Going out to look at it, it was unusual because we had a 1-inch asphalt bond breaker between the overlay and the older jointed reinforced pavement underneath there. In looking at this, there was actually a punch out in the middle of the slab, which was highly unusual, and couldn't really figure out what was happening unless the interlayer had somehow disappeared. Taking a core, yeah, that's what happened. I'm not sure how it could basically wash or filter out of the middle of a panel, but somehow it did. So we had settlement there. And in this case, you've got to go in and replace it. The nice thing about doing this with a concrete overlay is that if you take out the inner layer, what's left of the inner layer, you can actually add another inch or so of thickness to the unbonded overlay and just use a fabric bond breaker instead. So you're not taking up that extra inch with asphalt again. You could actually just use concrete there and come up with a thicker structural capacity for it. Depth of reinforcement, this isn't, and I should have prefaced my remarks to mention that I'm really just talking about scoping jointed reinforced or jointed plain concrete pavements. Missouri has not really done, well, we did one, but that was it. One continuously reinforced concrete pavement. We're not like Illinois or Texas or a few other states that do it more routinely. So when I say reinforcement, I'm not talking about the rebar that you tie for a mat of steel, like in a CRCP pavement. That's not going to float. It's not going to go anywhere. This is the mesh, a wire mesh used in jointed reinforced concrete pavement design, which quite a few states built pavements this way for decades, and we were one of them. You may wonder, well, why did the wire mesh float? Well, take a look at the high precision mesh placement. It's no wonder. This is probably from about 30 years ago, one of our last jointed reinforced concrete pavements that we built before we transitioned to jointed plain. But you can see that, once it was basically kind of a 2-lift operation. A spreader would put the first, 7-8 inches down, the wire mesh on top, and then a slip form paver would come and put the final 3 to 4 inches. When you had the curvature of the mesh from stomping on it this way, then the vibrator going over it when you're placing the rest of the concrete, there's really no guarantee where the mesh was going to be. So that leads you to have to check and find out. And here's a picture of spot checking the depth of steel reinforcement for the mesh. The reason why this is important is if you're going to consider diamond grinding, you don't want to grind a pavement where the mesh is too close to the surface. Generally, you'd like to see at least an inch of cover. There's more sophisticated, expensive ways of doing it. If you're just spot checking the pavement, I think nothing beats a cover meter. It's quick and easy to use and relatively inexpensive. And here's what I mean about high steel. In this case here, there's maybe 1/4 to 1/2 an inch of concrete that basically spalled off and exposed the wire mesh. If you go in and try diamond grinding this, you'll just aggravate the situation and make it worse. And the shame of it all is that structurally, the pavement is still in pretty good shape, but it's just a legacy problem of the mesh placement that we have to deal with the old jointed reinforced concrete pavements. So not everybody has those, but there were a lot of states that build pavements this way. Here's some minor spalling or shelling on the surface, and this is the kind of situation that I probably just ignore. It's not really impacting ride, and why disturb it at this point? Load transfer, if you dowel pavement joints like I think everybody should, I never really understood why some agencies didn't. I'm not going to point fingers or anything, but it just always seemed common sense that if you have joints in concrete pavement, you should have dowel bars across there. If you have an 1 1/4, 1.5 dowel bar across the joint, I mean, you shouldn't see any faulting or virtually none for decades. However, again, with the older jointed reinforced concrete pavements, you would tend to have mid-panel cracks, and you wouldn't have any reinforcement across there other than the mesh, which wasn't doing anything. You would have a loss of load transfer there. So that's where using an FWD or something to check load transfer is handy as far as establishing quantities. Nice thing about using the FWD is that you test a joint or a crack before and after you do some undersealing there to restore stability. You will definitely see an improvement if you plot the load versus deflection and you do the standard 3 different drop heights, or which represent 3 different load weights. You have a pretty linear relationship within that range, and you can compare before and after. So ideally, you want to see that line intersecting close to the origin, like in this case here, after you underseal. Here's a case of where we got faulting at a joint where we should have had dowel bars. Did a little investigating on this, and we noticed that the faulting increased as you went from the center line out to the shoulder. And after maintenance crew sawed this panel out right along the joint, what you're looking at in that lower right-hand corner is the embedment of the dowel bar on the leave side, or basically the downstream side of the joint. And you can see how little embedment there was. I mean, it goes from maybe a couple inches towards the center line to almost nothing towards the shoulder. Now, you don't have to position a dowel bar to be exactly halfway on one side, halfway on another side of a joint for it to work. But the conventional wisdom is you're going to need at least 3 inches of embedment to get appropriate load transfer. And obviously in this case here, we didn't get. Another situation is sometimes you'll have settlement and you could have actually a longitudinal crack that results in faulting. And this situation here is because we widened the road, put a retaining wall in to basically contain the roadway widening. The new fill material was not properly consolidated. And so what happened was there was a longitudinal crack that formed roughly at the interface between the old and new fill above there. In this case, we tried addressing it by doing some what I call heavy duty cross stitching with bars larger than you normally use. Usually you're cross stitching, you're using number 5, number 6 bars. In this case, we're using think number 8 or thicker bars to try to hold it together. Aesthetics, this comes into play to a degree. I mean, you can apply a bunch of fixes to a slab, may be cost effective and maybe addressing all the structural issues, but it could also look ugly as a mud hen too, as in the situation here in this exit ramp on I-55 where we did some slot stitching, which is basically doing dowel bar retrofits turned at 90 degrees, tie a longitudinal crack together. Anyway, in this case, we probably would have been better off just replacing the slabs rather than doing the stitching here. Speaking of mud, here's the mother of all mud ball projects. What happened here was normally at an on-site concrete plant, you're going to lay a sacrificial layer of stone, maybe about 6 inches thick or so, that you place your aggregate stockpiles on. What happened here, though, is evidently the guy operating the front end loader for the stockpiles decided to go ahead and use everything, including the sacrificial layer and whatever was below that layer, which in this case was a lot of silty clay. And so we had some mud balls that literally extended all the way through the full thickness, which I think was about 9 inches here. I mentioned mud balls earlier, and usually they're aesthetically maybe noticeable, but you can epoxy them or do something else. In this case here, these were just too prevalent, too deep, too big to avoid having to replace the slab. This was probably the most extreme example of a mud ball problem you're going to see, but it can happen as evidenced here. Cross stitching is a great, relatively low cost fix for longitudinal cracks that are still relatively tight and you're just trying to hold them together. But the one thing that can happen is the epoxy you use to cover it can either pop out, or in the process of doing the drilling the holes for the bars, sometimes you'll have the edge shell out, especially if the hole is too close to the crack that you're trying to tie together. That was a situation, that lower right-hand picture where you can see the epoxy is kind of spread out because basically you had to cover not only the hole, but also the spalled out area. Okay, last thing I want to talk about quickly is just estimating quantities. And this is more geared towards roadway designers or whoever's putting together the plans and specs. But typically you could be designing a project or repair project maybe a year, sometimes 2 years ahead of time. So you're pretty much guaranteed that there's going to be an increase in the distresses. Rule of thumb is maybe increase the quantities about 10%. Also, if you're listing specific repair areas, especially for full depth repairs, there should be some type of reference coordinates used, either log miles or GPS coordinates. That'll help the project office and the contractor locate them more quickly. You could also add other preservation treatments. What I mean is other pay items, because if you don't have a pay item, in other words, let's say you didn't set up partial depth repairs, you decide you were going to do some after the project is let. If you don't have a pay item for that, you're going to have to figure out how to negotiate the price, which may or may not be, you know, a pain in doing. So a lot of times it's good to have something in the, maybe a minimum amount of repair in the contract. There is a con, there's actually a con to doing that, but I'm not going to go into it. And then after the project is let, like I said, you had to add a higher quantity for repairs to anticipate new distressed areas showing up. And in that case too, it's typically the construction inspector that's going to have to go out there and locate those. This is where some education for construction staff is a good idea, even though they may not be well versed in pavement design or maybe on the materials side specifically. This will help them make the right call between, say, whether or not something needs to be a full depth repair or partial depth repair. And also a thing to consider is that, you know, the resident engineer, the project engineer, whoever's overseeing the project is responsible for trying to stay within budget. If quantities get cut, a lot of times it's going to be repair quantities, especially if something's going to be overlaid. You know, they probably figure they can get by without doing some repairs if it's going to get covered up. You know, there may have to be some discussion between the pavement designer, whoever worked on the plans, and the construction project office as far as negotiating which repairs to take out. So, and I covered a lot of different areas. You can go a lot deeper into some of these, but I just want to touch on some of the main points involved in doing an evaluation of a concrete repavement for restoration. That's it. Thank you.
The preceding was produced by the National Center for Pavement Preservation. More information can be found on the web at pavementpreservation.org. Additional support provided by Michigan State University.